Hello, my name is Oleg Klyudt. I'm working as site reliability engineer in Google. And I'm working actually in the team responsible for authentication and authorization of mostly web flows within Google infrastructure. Whenever you basically, every time you sign in, sign up, all this like cookie stuff, it's all go through our infrastructure. Plus, when you use cloud APIs, and normally it involves OAuth protocol or OpenID, it's also our infrastructure. Google Kubernetes engine, GCP, and whatnot. It's also there. Part of what my team is working on and supporting. So what's actually infrastructure that's all that built on? Mostly it's microservices. We still have some really big monoliths, but they're like mostly kind of legacy servers, which we're still working on splitting the microservices. Plus we have like tons of different databases. We have our own custom written Paxos key value store. So it's like globally distributed, externally consistent, and all that goodies that we wrote, still maintain, and still add features to. We have multiple of spanner databases. Ooh, it's quite persistent. Spanner databases, we do not like really developing them. We're mostly like a client. Plus, we have big tables. Big table is externally known as, well, there's an open source implementation of big table known as HBase. So what's the talk gonna be about? Basically, what is service mesh and system reliability goals from this talk point of view. And then we'll talk about best practices in the service mesh. Best practices ensuring system reliability and how they affect system design. Because you'll see that quite often it's should not be left as afterthought. You must really plan for them. And some key takeaways. So first of all, what's the service mesh? Here I just drew some simplistic pictures, something to kind of keep in mind whilst we go through the talk. It's basically like multi-cluster deployment. We have here, so basically Ingress, some, incoming HTTPS load balancer for the cluster, and because we have here multiple cluster, it can do cross clusters load balancing. Couple of front ends, you can think some, one is giving the user the HTML page, and another is exposing some REST API, some mixer server, some kind of a middle end which abstracts away particular implementation dependencies. It might have egress, which is very common, if you have in your infrastructure some service. External one, you talk to it. It might be, some logging API, or we just basically send off the logs, or you can use some cloud spanner and talk to it, or whatever. Basically, when you have to talk to internet. For the sake of illustration, it has cache, it has backend, which is actually abstracts away all the peculiarities of database management and hopefully serves as an adapter. So basically, that's the service stack. It mostly looks as its set of monoliths. That's intentional to keep a bit picture simple. In reality, like what we have, one kind of a stack, it has around 100 microservices, because it's not one front end, it's like 10 or 20 or 30 of them for specific purposes. So, and what's about service reliability goal? So from like site reliability perspective, there are two main goals as I define them. First is satisfy all demand, and what it means basically, all the incoming requests to your stack. Demand all the requests users send to you, being that external users, be that internal users, because you can provide services within your cluster, there are cluster tenants. And what you want all those requests to be served, not just shed them. Oh my God, I don't have capacity, and that it means that you have to actually have capacity, plan and provision for it, and it involves making use of that capacity so that you don't end up a situation like you have capacity, but you cannot really make use of it because of over provisioning factor or whatnot. And yeah, that's all in the domain of satisfying the demand. I'm not really gonna talking about that because it's mostly about capacity planning. Instead, I'm gonna focus on this talk second goal: serve within error latency budget, basically within a SLO. And here is a key idea: is that how do we define service reliability? Like, it's impossible to have a service which serves no errors. There will always be error. How many errors would be like, too much or not too much? Good answer to them is to define basically SLIs, metrics, SLO, how much error margin you allow, and basically make a judgment call within those metrics. You allocate your service SLO budget and work with that one. And the point here, you see that, it's kind of intermixed, errors and latency. Why? And it's very important to understand that in practical systems, it's quite difficult to provide this law only on errors or only on latency. Because if a user sends you a request and you're taking like a minute to process it, a user doesn't care anymore. It's an error. Even though after 30 seconds or a minute you can give it back. So after some timeout or some deadline of request, basically latency is degrading the errors. And so talking about best practices. First, as I call it, in DC and cross DC load balancing. Basically, once you have one single deployment, some very big Kubernetes cluster, you can call it a in DC load balancing. That's what mental picture to keep in head. Otherwise, it's cross, for example, Kubernetes cluster load balancing. So first of all, why we want that? Of course, first is a key to scalability. Because quite often it's especially the case for stateless services or fungible replicas. When you want to serve more capacity and your service replicas are fungible, then the easiest way is to add more replicas of the server. Oh, now I had 10 front-end tasks now, pods, now I have 20. Then it's a goal and job of load balancer to actually load them with the traffic. And here comes another important concern is that ideally we want to equalize load across them, depending on load here it's what request is upper bounded or bottleneck resource of is, for example, CPU. You want CPU utilization across the pod replicas to be roughly the same. It was a great, the previous talk from the Kiwi team about that. And another, why? Because we want to have keep latency low. It's especially the case when you have cross-region or cross-zonal replication of a service, and you want to serve a request in a location or in a cluster which is closest to the user. Because basically all the latency is composed of the RTT network latency and the processing latency. At least you can cut down on the network path. Key concept here and idea is prefer L7 load balancing. That means at application level so that it can inspect the protocol. What it gives you? L7 gives you finer load balancing granularity. Compare that if you can load balanced, you have pool of tasks, and you in round robin, weighted round robin, you name it. You load balanced request on per request basis. First request goes task 1, second request goes task 2, and so on. You can't do that at level 7. You cannot do that at level 4 because then you have a connection, and then connection kind of not really the same. Some clients can send you like thousands of requests per second or just almost nothing. What it also enables you to do is content-based routing dispatching, because it allows you, this L7 load balancing, to see, if it's RPC, remote method, remote call, or it's HTTP, URI, and all that information is available to you. It allows you to do, for example, traffic splitting based on the request path or service, do selective drops, which are very important in when service is melting down over global overload, and so on. That is what L7 enables you to do. Of course, it has some assumptions about that request should be processed relatively shortly, and that they are not stream-like. Otherwise, we are basically degrading to kind of L4 load balancing. And stream-like can be maybe WebSocket, or if it's some encapsulation over L7 of some stream of video upload or whatever. Then here, how do you really balance the bytes? And here's the picture. Basically, so that you have an idea. In Kubernetes, when you read documentation, you'll get a concept, oh my God, there's Ingress, and just allows the traffic in, and then the traffic kind of contained within my cluster. Yes and no, it depends what you really want. It can be configured like that. Like here you see you have a global ingress, and here you have 2 clusters or 2 regions, 2 zones, whatever. And once traffic entered there, it stays there. If it, as it goes down the stack, some component failed, it refused to serve it, game over. Or you can actually enable, oh God, you can actually enable cross DC load. Okay, I didn't really read it. What you can do is for every, basically, it's a service mesh. For every service, you can configure cross-regional, cross-DC, cross-whatever locality load balancing. There is no, good, there's trade-offs here. One of the trade-offs, capitalizing on the last point about intra-DC versus cross-DC load balancing, is that blast radius containment. Some services, they are prone to so-called query of death, especially something like search, or where a user can enter or provide you some arbitrary craft. Sometimes, if a user sends you a request and your server dies because of whatever, then normally user side has a retries, it's another request, another task dies, and oops, all of the cluster is gone. And if you don't, if you have at every service level, basically, global load balancing, a failover, that's a very good way to a cascading failure that will just obliterate your service. Because it takes time to restart a node, to do like initialization and so on. There are, of course, strategies to prevent that, but it's something to keep in mind. And that happens when you don't have cross-regional isolation. When you do have such cross-regional isolation, meaning like on the previous cluster, you do not allow this, from frontend 2 to go to the mixer node cluster. So basically, yeah, the user requests can drop, in the worst case, take down one cluster, but at least, your users in North America or in Asia, they are routed to their own regions, and they will be able to still be served, under the assumption that global ingress doesn't do global failover. So it's a trade-off. But also, like, once we start talking about cross-DC load balancing or load balancing across multiple targets, here comes the concept of an idea of capacity. Now it's not one target, and you just, round robining around it to equalize utilization. You have basically, for example, 2 services, and you have to somehow balance across them. So capacity, and you normally, so there are 2 algorithms for regarding to in-cluster or cross-cluster load balancing and playing around with the capacity. First is waterfall by region. Idea is simple. So there is a user, it sends a request. There is a cluster, serving cluster next to the user. You want that cluster to serve the user request, given that it has enough capacity. If it does not have enough capacity to serve the request shall fail over to the next closest cluster, which still has capacity. If that one doesn't have capacity and you still have something to fail over, it will. Otherwise, if all clusters are full, then it enters, for example, envoy documentation of load balancing proxy says as it enters like panic mode, it just throws the request somewhere. Or you can configure a drop overload, then it drops it. So yeah, as I said, location failover, we've already covered. What also this enables you to do, which is a very powerful idea, is error-averse load balancing assignments. Where it helps, imagine you have a cluster. Basically, you have 2 clusters, and one cluster starts serving a lot of errors. If you just statically configure that capacity on that cluster, then you'll be throwing queries there until the capacity is configured static limit of requests per second is reached. Or if you, for example, based on the CPU utilization, cluster capacity calculated to be dynamic, you don't want to configure that manually. Rejecting requests, for example, or failing them normally is much, much cheaper than serving them. Such cluster can become a disaster and sink more traffic. What helps in these cases is error-averse assignments. The idea is first that if a cluster serves errors, meaning you track the number of requests being served and also number of errors being served, the more errors a particular cluster or service location is serving, the higher cost for per service request becomes. Essentially, the more errors, the lower the capacity of the cluster is. That helps you artificially inflate the cost of the request, deflate the cluster capacity, and create a failover. Where it helps a lot? When you do, for example, rollout of new binary cluster by cluster, and shit happens, it has a regression, some bugs, starts serving a lot of errors. It helps you because you do cluster by cluster. In the first cluster where you rolled it out, it starts serving errors. Its capacity is decreasing. So more and more requests are starting being served from another location where you did not roll out your binary or release 2 yet. And that helps avoiding extra requests being served with errors. Of course, it assumes you have monitoring, alerting, your SRE of someone is looking at that and trying to fix that or roll back the binary. Yeah, and very nice features about auto-scaling. As I mentioned, this averse assignment, and there I mentioned that you can configure the cluster to derive its capacity based on the cluster service replicas CPU utilization is CPU if the bottleneck resource for serving the requests. So using the CPU usage, you can calculate capacity automatically, and that plays really nice also with auto scaling. And here I'm basically mean horizontal auto scaling, because you can configure that. Oh, you know, if my cluster service in the cluster serves request and its average CPU utilization is above 80%, add more replicas. So what happens? You're adding more replicas, and the effective cluster capacity increases, because why? You're adding more replicas, average CPU utilization drops, and because you derived CPU cluster capacity based on that value of average CPU, cluster capacity increases. It plays really nice with load balancing, and you know, absorb some requests like legitimate or DDoSing and stuff. And traffic black holes is what I've just discussed. When static limit is configured or not error-averse assignment is configured, can very well happen that the cluster will suck in all the traffic, and where's traffic is gone? Nowhere, it's just being dropped. And there are a couple of even worse cases where if you use, for example, this CPU-based cluster capacity calculation, you will notice that it's kind of a feedback. You know, more traffic is sent there, CPU utilization increases, and it also affects traffic capacity. You'll notice that in this degraded use case, it can consider that as a stable condition when it basically rejects all the requests. And because it's so cheap, the clusters seem to have so much capacity, let's throw everything in there. But we just basically discussed that. For traffic black holes beyond error-averse assignment, what also helps you is to have health checks on the service constituent pods or replicas and readiness probes. Health checks and readiness probes, by the way, is a terminology of Kubernetes. But the idea is basic, is that there should be some kind of a signal which the service replicas gives you back, like, hey, I'm healthy, I'm ready to serve the traffic. And the load balancer, or whatever logic you have there, which consider task as eligible for load balancing, looks for that signal. Once a service pod or service replica is healthy, it starts replying to the readiness probes. Load balancer knows, aha, I got one more candidate to load balance the incoming load onto. And now talking about overload. So first of all, what is overload? Basically, it's when some of the resource is exhausted. And the resource can be like hardware, you know, not enough CPU, not enough memory, or it can be some internal resource which is running out. The simplest example, you have fixed thread pool size and fixed and bound request queue. Once they saturate, server cannot really serve anything anymore. And or you might have some mutex contention and some concurrency stuff, which is blocking serving the request. It's also kind of an overload. And here it's a curve I measured on the typical server. It's asynchronous servers, so all requests asynchronously. And you'll see that what happens is that on horizontal line there's like QPS or queries per second or requests per second, and on top there is serving latency. And you see that, you know, the serving latency here is like simplistic server, like, I don't know, less than a millisecond, just, you know, return value from memory, until some QPS is kind of a limit is hit, then it just booms exponentially. So serving latency grows. And once it reaches some, you know, once you add even more load, while it stops here, it crashes out of memory. And so that overload, where it can happen? It can happen on single like task, on single replica, on single host, right? It can happen to all replicas of the service, or the worst case can be global overload. And some of the causes of that, you know, it can be loss of capacity. Loss of capacity means there is no serving unit of that capacity. Maybe it's unavailable, you know, misconfiguration, it keeps restarting. Maybe there is some bug, for whatever reason, its dependency is not ready, it does not answer a readiness probe, so a load balancer does not consider it healthy. It's all leading to loss of capacity. Another reason is malicious or legitimate traffic spike. You can like easily imagine that, you know, it's some New Year Eve, a lot of people going to, you know, for shopping or whatever, and there's just spike of traffic to some e-commerce website or something like that. It's like good traffic. You do want to serve that. It gives you money, right? But it can create overload to your infrastructure. And of course, there's always bad players out there. There's also internal amplification. Here, mostly what meant is when you have some misconfiguration within your network and there's some traffic loops. Another interesting internal amplification is if you have a service with high fan-out ratio. Fan-out means, I received one request, and sometimes depending on the payload in the request, I can send out one request, 2,000, a million. And in kind of normal steady state, it can be not a big deal, some spikes here and there of utilization. But in some degraded scenarios, when it happens that you start receiving a lot of these high fan-out requests, you're basically starting overloading the server and basically all the serving tree beneath it. Oh god, this is my favorite one, excessive client retries. Worse, it's synchronized. Whenever your service has a blip of an availability, client retries will always make it worse, because there are always out there clients who just keep retrying whatever the cost is, every second until I get a reply. I don't care about that service. Many of them don't limit the number of retries. Many of them don't use kind of randomized jittering. You had an availability of a second. You can expect in a second get all the clients, then in a 3 second get all the clients, then like 6, and and so on. Because when clients don't implement this randomized jitter, they're getting synchronized. And of course, I mentioned the deadlocks and resource exhaustion. So how can we prevent that? Know your system constraints. That basically meaning that you have to realize in your service mesh what is the bottleneck resource of your service mesh. Is it RAM? Is it memory? Maybe service is really like bandwidth, demanding. Maybe IOPS number is the bottleneck, because then you can prognose what the badness can happen to my service. And once you know what's the limiting factor, what's the bottleneck, do load testing, because then you know how the system reacts. For example, that picture, right? When basically the server got like tons of requests and eventually crashed. It's only applicable to server which load the CPU bound, and it has much more memory, and it also means like it's load the CPU bound, requests are small, so that the more requests you get, it basically more CPU is being spent on them until some cap on CPU limit is hit. Then you're being throttled by completely fair scheduler or whatever on some other thingy. Because it's getting throttled, like you cannot serve that many requests anymore, so latency of all of them grows. And as you keep receiving more and more requests, you eventually crash out of memory. It's like, for example, case of C++ binary. With native memory management in Java, you can get like, oh my god, I'm like out of heap exception, something like this. Two other common causes, change canary, when you're deploying new binary release, new configuration, new dynamic experiments, whatever, causing a change, do canarying, meaning like, don't go fast and furious deploying it everywhere and hope for the best. Roll it out to something and see, have some kind of A/B testing, or just basically look at the metrics if you don't have any automated system to see how it works. And basically, gradual changes rollout goes into the same basket. I already told about control client behavior and retries. If, of course, those are external clients and you don't provide them some libraries to use your service, they're going to have bad retries. You have to deal with that. Build, for example, be building like throttling per client or some quota system per client, or rely on existing services. If, however, you consider, again, your service mesh, some other services within the service mesh are your clients. You control them, you program them. There you can set up adaptive client throttling. The idea is simple. So if a service A talks to service B, and it has some set threshold of maximum error ratio. Once it sees, for example, oh my god, to this given server, all of a sudden I'm seeing 1% of my request with errors. It starts slowing itself down, so that it slows itself down with the hope that error request ratio drops. There's like adaptive client-side throttling. Of course, horizontal vertical autoscaling is like, I cannot overemphasize it, is the feature to use. Because especially horizontal one, especially useful, of course, for stateless servers, or stateful, but which is still somehow fungible. We just add more replicas in there, and load balancing take care of the rest, spreading out the load. Vertical autoscaling also works. That depends. You can actually have even both, because imagine if the overload is by some request which has like super big, I don't know, payload, and it like your server kind of crashes out of memory. In this case, vertical autoscaling, which would notice that out of memory errors and will add you more RAM and will reschedule the pod, is actually the answer here. Another very useful thing is that we see it quite often that there is some holiday season, there is a prod freeze for a couple of weeks, and your services are running, and you see how their memory is leaking, some badness keeps happening. All of a sudden, these dead tasks or pods start serving requests with some crazy latency. Of course, long-term solution is trying to figure out and fix that. In the meantime, well, you can try either the simplistic approach, randomly restart service tasks, of course, with rate limiting. You don't want like that. Going and restarting all your cluster. For example, Netflix Chaos Monkey is one of these tools. You can be more sophisticated, trying to detect outliers and restart them. So those were preventive measures. About reactive measures, drop or block excessive load or clients. It's especially powerful when you use L7 load balancing, for example, in Envoy proxies. You can configure and push some of the rules that, if the content of my HTTP request or gRPC incoming request matches this, just drop it. Second, if you don't have autoscaling or, caveat, your autoscaling is very slow, and so it doesn't really help you to add more capacity. Well, bad luck. Scale resources manually, if you know what you're doing. And the last one, disable readiness health checks, basically which tell the server that, tell the load balancers that I'm ready to serve the traffic. The trick here is that in case of overload, and it talks about like global service overload mostly, your tasks, yes, they are overloaded. But they're still kind of doing useful work. And if you just restart it, you basically you've lost a unit of capacity, because again it takes time to to start it, initialize, warm up caches, whatnot, JIT throw the code and be kind of productive again. So in some cases, not always, it makes sense to disable these readiness checks together with, for example, dropping some portion of the incoming traffic, because first you depressurize the load on your common service, and yet because you disabled readiness health checks, you do not let you don't let your load balancers to discard those slow replicas as not serving. They are serving the request. Well, another question is, will the user really be waiting for them? But we'll talk about it in the deadlines propagation. Another important aspect of reliability system changes. So what are these? Pushing, it's system changes, and there are some of the bad practices. They might or might not apply to you, but it's something that we found our developers are doing, and well, previously, thankfully they're not doing that anymore. Some of the stuff, push local changes to code and configuration to test or the production. Just, like, oh yeah, I can kind of fix that bug, wrote something, push to the production. Then something is wrong, like, what changed? Where is that code? You look at the code base, it doesn't make sense. That's why. Also, pushing configuration from hand. What we found working the best for us is when we bind at the, for example, build time, or when we're creating a release. So we build a binary, we take a configuration for that binary, the configuration, basically all flags, all our arguments, all options, you name it, which controls behavior of the binary. And you package them hermetically together. So it's kind of a one deployment unit, and you progress with the deployment unit across your fleet. If there is a regression, you need to roll back. You're rolling back also in these kind of atomic units. Why it's important? Because sometimes in code you introduce new features which are activated by some argument, and then if you don't have this kind of a coupling between the binary and the argument, what can happen is that you roll out a new release. Oh my God, there's a regression, and then there's a config which is activating that feature which is only available in the new code. So you roll back the binary, but you did not roll back the code. Now the binary cannot parse incoming flag or incoming argument, and it gives you a dud. Basically, like, oh my God, I cannot serve. Let me crash. And yeah, I mentioned already, pushing globally as fast is a bad idea. canoring we've covered already. Fallback logic, it's a very important one. So basically, we all want our service to be reliable. And sometimes we build logic, for example, so if this particular bad case happens, I'm gonna be using like this kind of a fallback, you know. Maybe I'm gonna serve integrated mode. Maybe I'm not gonna really use that backend, I'm maybe gonna use that kind of a slower backend, you know, you just name it. Basically, it's safety measures against bad cases. However, the caveat here is that quite often these configuration knobs or these code paths, they're cold, meaning, you know, they're designed for cases which happens rarely. Yes, they can be covered with unit tests and integration tests, but will they really work in the production? That's a big question. And really good practice is basically exercising them all the time in the production. You know, when the binary loads, try to exercise this fallback. Does it work? Okay, I'm going back to my main path. Something like this. Because we really had some really unfortunate incidents where fallback logic, which was supposed to help, made the situation only worse because it was cold path. Yeah, and based on those bad practices, as we found them within our infrastructure, we treat config always as a code. It always goes into central repository and so on. They're hermetically bound and pushed together. Also very important, production changes logging. You want to know what happened in your production. Which binary release got updated, you know, who pushed that, what traffic changes were activated, and so on. Monitoring alerting goes without saying. Yeah, this thing crashing binary on startup is okay sometimes. Here's the assumption is that, for example, in Kubernetes, when you create a deployment and deployment starts, you know, actuating and deploying it, what you here basically rely on the fact that if deployment tries to start a new pod somewhere to schedule it, and it sees that pod fails multiple times, these liveness checks, you rely on this controller to abort the deployment and roll it back. And it's actually a nice feature because it can help you, you can deliberately use it sometimes to say, okay, you know, if there is a regression which crashes my binary, for example, I know that, you know, the deployment scheduler controller gonna roll it back. Oh yeah, data consistency or inconsistency. So the main idea here, please prefer strong consistency for your data, strong external consistency for your data. That, yeah, talking about what it really means, gonna take another 40 minutes, but idea is that what you really want to have is like one computer, even though it's replicated, you know, for fault tolerance, all that stuff. It's like one computer, so you know, whoever of the clients writes to it, a lot of clients can immediately see that effect. So it's basically what we get from one machine. Well, discarding all this like cache synchronization and so on. Imagine one big machine, like one CPU, one core. And it's not only one machine, it's immensely big, huge machine. So it's scalable, you know. Or right, you know, like I got data from 1 gigabyte to 10 gigabytes to 1 petabyte to 1 exabyte. Just throw it in and it's gonna serve them. It's ideal case, it's what we want to have. Why? Because eventually it simplifies writing the code logic. You know, originally we had a lot of the deployments on big tables or on other eventually consistent systems. This inconsistency, well, absence of an eventual consistency creates problems and very hard to debug bugs. And sometimes we had very severe incidents because of some really like edge cases having to do with the eventual consistency. Plus, if the client, you know, first when you create that application, you wrote the code, you thought, I don't need strong consistency. Then application evolves, you know, business requirement changes, and then all of a sudden you see that, oh my God, I do need actually strong consistency, otherwise I can provide this or that feature. So, but the storage system cannot provide you that. So what you do instead, you start creating some hacks, workarounds, passing around consistency tokens to ensure, right, like read your writes or something like this. It's all nasty hacks. If possible, you know, prefer always strong consistency. Problem with originally with strong consistent databases was that they were not that much performant. So that's why, you know, all this hype about NoSQL and so on. It still has its uses, of course. But recent developments on, like, for example, on SpannerDB, once that paper was published, there were a host of spin-offs. There is open source CockroachDB, which provide strong external consistency, and they're globally replicated. They're automatically shardable. You know, if you load your old data on one particular shard, it will basically be auto sharding it. So you can basically end up with one key on one shard. so that it can accumulate all the loads. So these solutions are available. If you can, try to use something like that, because it facilitates code, and you spend your devs iteration not on how to create an inconsistent data workarounds. And also bear in mind, storage migration later is always like a very costly effort. Okay, across the stack work conserving. Yeah, the main idea is that avoid doing the work which clients don't wait for anymore. Good example, deadlines propagation. On the incoming, as the user request comes to your stack, you attach some deadline to it, let's say, I don't know, 30 seconds, 20 seconds, 10 seconds. And then it propagates across the stack. It came to the front-end node, it spent there, say, 1 second, and initial deadline was 30 seconds. Then it leaves that node and has remaining deadline 29 seconds. And this story repeats across the stack. How it helps is that if the service, if the request deadline has been hit, it just cancelled locally. You don't need to propagate this kind of notifications, cancellation information like anywhere. It just works. Work is cancelled locally. Caches, here the story, we're running out of time a bit. The story here is you can have latency caches and capacity caches. We know what the caches are used for. But once you have a very high cache hit ratio, you see, wow, but that capacity which I used before for serving requests is now being used from the served from the cache. Can I really remove that capacity? Like, it just, do I really need it? At that point of time, your latency cache becomes capacity cache, because if it melts down, request hit ratio drops significantly. All that load will just as avalanche go to your main service and can cause global overload. Here it's very important to create have some circuit breakers or limit how much of the cache misses you allow to be drained into your system. Observability is very important. It's mostly about monitoring and exposing metrics, scraping them, and very importantly, having distributed tracing. Distributed tracing, especially in service mesh, allows you to understand what happens to requests, what's all the root. In a typical deployment, you can have not acyclic graphs. You even can have cycles and the dependencies. Distributed tracing is the answer. And dependencies are unavailability, the last point. So it's very tempting, to declare, so my service cannot serve anything if these particular dependencies are unavailable. However, it's quite often not entirely true. Even in microservices, where basically your service can be, you don't have a monolith with 10 services, but even with one. Maybe you still can serve some of the requests. And avoiding hard dependencies eventually brings you more stability in your system, because if one dependency is unavailable, then in the worst case, all your cluster be unavailable, and not because it cannot serve the request, just because it basically lays down. It cannot be even scheduled. It fails pods readiness checks or liveness checks. So the best case here, like what to do about the situation. Declare them, try to make them soft dependencies, try to sort of degrade it more. Okay, if you have hard dependencies, let your service pod start. Maybe so that they do not fail liveness checks. So, Kubernetes scheduler do not reschedule them as ping pong around the whole pods, stuff like this. But they might not reply that I'm ready to receive traffic, meaning the readiness checks to load balancer. And once their dependency comes alive, this is not already initialized. It can serve the traffic. It can say, hey, I'm here, I'm ready to serve the traffic. And it's off the go. So key takeaways, I know there was like really, really a lot of material. Important one, ensure cross-stack observability. Monitoring, per service, and distributed tracing. Second, use L7 load balancing. It provides all the goodies you need for prevention and the reaction to overloads. Auto-scaling is net win. Vertical, horizontal, plus if you use some of the cloud offerings, Kubernetes clusters, they even provide you with cluster autoscalers. And always prefer using externally consistent DBs. And as an overarching idea and thought, always try to do work conserving, use work conserving approach. If you have some limits, don't on limited resources, don't enforce them just because it's set, if resource is really available. Only start enforcing limit when resource is approaching its capacity. That's work conserving idea. Yeah, and I'm open, of course, to questions. I expect a lot of them. Actually, some of the things I talk here, they covered in a lot of depth in the site reliability engineering books. I invite you to take a look on them. Yeah, I won't be commenting on these slides because these slides list basically implementations of the ideas, which technologies you can use, and here and for tracing, for DBs, for work conserving. Just too much stuff to talk about. But yeah, take a look. So that's all for me, and I'm ready to answer your questions. Yeah, I see a hand there. There's also a hand here in the front.
Okay, thank you. You mentioned DC tracing. Could you tell me what you use for DC tracing? Is it open source decision or some internal one?
That's a good question. So there is a published paper, I think around 5 years ago. So the system is called Dapper. Once that paper was published, there was like a boom of open sourcing activity to implement something like this. I think, the very well-known one is Zapkin. But then they started kind of other, initiatives spurring around. Then there was a realization that, yeah, they kind of implement these ideas, but they're not kind of interoperable with each other. Then they came around this initiative Open Tracing, which provided kind of a set of consistent APIs which clients will kind of write their code in adherence to, and any implementations can write their basic implementation using those APIs. Here's listed some Jaeger, Instana, Lightstep. Basically, those systems provide you both the storage and collection of traces, and they provide you libraries consistent with Open Tracing API to attach tracing information and to propagate tracing context throughout the stack. There is another thing which is called Open Census, which takes a bit different approach to this one. It, instead of defining API, it actually provides a set of libraries for all the languages which are doing distributed tracing and which are also doing the monitoring. And it provides the exports to all of these, for example, Jaeger, like Stackdriver, and Prometheus for monitoring, for tracing, like Lightstep, and so on. Basically provides driver to all the backends which actually store, process, and grab those results. So here's basically your answer is look at the implementations of Open Tracing API, and there is the implementation. It's not Open Tracing API, it's Open Census.
Yeah, thank you.
Yeah, there's. Yeah.
How did you log it? For example, you said about pod container history.
Mm-hmm.
For example,
mm-hmm.
I did the change in production set.
Mm-hmm.
Did you store it in Git or something like that?
Yeah, okay, I got it, yeah. So what we have internally, it's basically kind of a searchable key value store. And it provides effectively some interface to inject, events about something happening in the production. And all our internal systems, including, for example, this analog, like in internal Kubernetes is Google Borg. So Borg master, which will be like Kubernetes scheduler master, it integrates with those. And when it receives a request to start a job, it has this information about the binary, the configuration. It provides basically it uploads all the configuration there, so that not only you know what was pushed, but also you can, meaning you know not only that event that something was pushed, but you know exactly the configuration that was pushed. Plus, I didn't talk about it, we have internal audit and provenance verification of the binaries. So you always know, remember Google has a global single repository. So you always know at which change list or at which repository version the binary was built. So the build is always reproducible. It's signed. It's attached the provenance information, meaning who built it, which changes it included, change log, integration log, and all basically of that meta information is also uploaded there. plus configuration. And even if the clients did something, sneaky, like, let me write some, changes to my code a little bit locally, and also changes to configuration locally, and let me push it. Depending on configuration, we're trying to steer away, to prohibit it completely. Sometimes it's still allowed, and there are use cases for that, like test. We want our developers to have rapid velocity and this stuff. Still, the scheduler of job, or like in this case in Kubernetes, scheduler for the pod replicas, it will log all that information, who did it and what the actual, even local changes were. Yeah, basically, it boils down to integration across whole your stack to the instrumentation to log. Yeah, there were other questions?
Okay.
Yeah.
Thank you, Oleg, for your speech. Very useful information. My question is about reactive merges. Could you open, please, slide number 16?
16?
Yes.
Yeah.
Last option was disable readiness probe, health check. Is it choice between two evils? If we disable readiness probe, we have increased error numbers, but of course we decrease overloading, but increase error numbers. How do
it's a very good question, because you spotted correctly that it will increase errors number. That's why I meant. So that's why it's kind of a last resort measures which we kind of start using. It's not common reactive tools, no way. And it's only used when there is a global service overload. You're already throwing errors like everywhere. Your service is melting down. And in this case, it also has to be used with some other preventative, not preventive, reactive mechanism like dropping the load. Otherwise, yeah, you will disable them. And so what? It keeps serving the errors and damn it! I forgot that I forgot to mention about load shedding. We also have the load shedding for services which CPU bound. They basically track their CPU utilization, and once you can configure it around 95% CPU utilization or something, they start shedding the requests. Plus, there is internal built-in logic in the gRPC we use internally, so that the client retry if particular task got overloaded, but they will try another task, plus the number of retries of a client is limited. Because you remember I was talking about the problem when on availability, clients start doing the retries, which makes everything worse. One way to address it, as we did internally, is limiting number of retries, plus limiting number of requests a client generally can retry. For example, we do not allow, I think, more than 10% of all the requests service A sends to service B to be retried. Yeah, because even with a budget of 3 retries, you can in 3 step, it will be exponential load growth, and can obliterate your service.
Thank you.
Yeah. So yeah.
Great talk for very, very hard to solve problems, and it took you a lot of years to fix all of this and figure it out, and you wrote great books on the subject. So I understand most of the things you are saying, but at the beginning on the first slide, I saw that you're part of the team that's in charge for authorization and authentication of the Google team. So I'm sure you know that if you have a secret and that secret lives forever, it will eventually leak out, and people need to rotate their secrets. And secret rotation, I guess, is a hard problem to solve. So I'm interested, how do you address that problem?
We have our internal secret rotation, and it's tough. For example, one of my projects has been working for past half a year. It's to migrate our push configuration for secret rotation from like legacy system to a new one. And because of the secret rotations and how basically about state superposition, because when you rotate secrets, you have to create a key, ensure that it's everywhere available, then somehow trigger the key, and there are many intermediate steps. It's hard, annoyingly hard, unfortunately. Yeah. So because it's hard, you'll see that there was a team here. Which was doing the talk about basically they're managing their secrets for you and doing the rotation, like user passwords. Plus, there are generally some as open source kind of services which can do it for you. At least they advertise. I never tried them. Plus, there's some public offering. Yeah, it's unfortunately a hard problem and takes a lot of resources to do it correctly and right. Yeah.
Okay, thank you.
Any more questions? By the way, guys, one thing I forgot to mention about, unfortunately, what hard dependencies, another problem they introduced. When you're trying to do whole your service mesh turn up in a new cluster, or basically somehow replicate it. You got a new cluster, you want to turn up your whole service mesh there. If they have hard dependencies, they do not want to start, or even worse, they're crashing if the hard dependencies are unavailable. What you have to do then, you have to basically figure out all that graph of hard dependencies and basically start them up in reverse manner. Super annoying, super annoying. It's insane. And if you use the hard dependencies, it's something that you have to somehow solve. I mean, of course, it's all solvable. It just creates extra work. Another thing, here in particular, what one can do is that, yeah, okay, there are hard dependencies. The binary will start, but it will not answering the load balancer kind of a probes, will not be participating in accepting any traffic. It will wait basically all the service mesh for all its hard dependencies to be ready. And once all its hard dependencies are ready, it starts answering that, hey, load balancer, I'm open to serving the requests. So that it's not without kind of its drawbacks, because sometimes people want to have, like in a lock step, here my all service mesh is yet not ready, and here it's all ready. But this kind of approach, services will be seeing that their hard dependencies are satisfied and start opening its serving port for load balanced traffic. It kind of eventually converges to the discovery of the service. And of course, if you have something like only one route, which is one kind of a front end, and here's a tree, that route will become available and start serving requests. The situation gets messy when you have multiple routes, and a request can get first here, then it will expect another route to be available, but it's not available because there's some kind of dependency here which is not common with that one, and still waiting for it. It's getting tricky. Yeah.